Hey, it's Jag. This week I'm taking a break from the Triwatt amp build. I'm not exactly taking a break. I'm pushing through this week and I'm going to get the whole thing built and ready for testing. So the next video will be all about that. In this video I show you two ways to identify the outside foil on foil capacitors.
Hey, how do you think they keep the airline pilots and astronauts from noticing a whole country is missing? That boggles the mind. I think if airplanes and spaceships are real, somebody would notice a whole country was missing. Maybe that proves that the Earth is flat and we really can't fly. And you know, I can't find any information online about how marshmallows were invented. I think the satellite pictures, I think they use the Photoshops. I think they're really good at using the Photoshops to put a country in the picture. So anyway, why doesn't? How come it's not pronounced doesn't? Anyway, why doesn't anyone notice that a country is missing? You know, I think I need to investigate about who invented marshmallows. What?
As I said at the top of this video, today I'm going to show you two ways to check the outside foil of foil capacitors. Why is it important to know where the outside foil is? It's not end of the world, oh my god, I killed my amp, important to know. As a matter of fact, some people don't think you need to know where the foil is, the outside foil is at all. But for those that do, and I do believe it's important, it's because the outside foil also can serve as a shield. So it can help eliminate some induced hum and noise and whatnot in your amp, especially in high gain amps where you've got lots of stages cascading into one another. That noise, no matter how small, adds up through every stage. So in that respect, it's important to know where the outside foil is on a foil capacitor. You want to put that side, the lead that's connected to the outside foil, to ground or to the low impedance, the lowest impedance side of the circuit, so that it has a chance to drain off that noise to ground. If you look at the schematic here of the Triwatt, we'll use that as an example. I'm just waiting for my screen recording to start. There we go. You see here is essentially the preamp section of the schematic for the Triwatt. You see our inputs all over here on the left side, and you see that the grounds go to chassis ground right here. We also see your high voltage rail, and they come in and power the tubes through the plates. You also will notice that the cathode resistors and bypass caps down here also connect to ground. So what we have here is your signal comes in, for example, through this jack. It goes in through this grid resistor into the grid of the first stage of your amplifier, your first gain stage. That is pin 2 of the triode. 12AX7s are a dual triode tube. That means essentially they have a triode on each side, or an amplifier on each side, or something that could be configured as an amplifier. Here, the input coming in here is going through this grid resistor into this grid, which happens to be pin 2. That's for the first triode. You also see that the cathode here, pin 3, goes down here, connects to a resistor, and then through to ground. There's also a bypass capacitor there. Here is your high voltage power rail. It comes in through your plate resistor and then comes to the plate, which is pin 1 on the first triode. The other triode of the 12AX7, we have the plate on pin 6, the grid on pin 7, and the cathode on pin 8. So again, we see there the power comes in through the plate load resistor to the plate on pin 6. We have this input coming through this grid resistor into the grid, which is pin 7 on this side of the triode. And here again we have the cathode on pin 8 going to a cathode resistor and then to ground. As you can see here, there's a little note, see tweaker's notes. You can mess around with your tonality by putting different values of bypass capacitor around here. We'll talk about that in another video. You can also change the gain of your stage by adjusting this cathode resistor higher or lower depending on what you're trying to achieve. So as I said, the signal comes in through the grid, pin 2. The cathode sets the operating point and basically allows your signal to swing positive and negative into the grid. So the plate, the power comes in through the plate here. Also, your signal goes out of your tube through the plate. So the signal comes in through this grid, goes out through the plate, and then goes this way through this coupling capacitor, and then on to the next stage of the preamp. You've got your volume controls. These are those mix resistors I talked about in the one of the Triwatt Build videos, and then they go into the grid of the next stage. So when we talk about putting the foil side of a foil capacitor to ground, that's pretty obvious, or to the low impedance side of the circuit. That's not quite as obvious. So when we look down here, this bypass cap right here, it connects to ground on this side, so we want to put the outside foil of the cap here to ground. For the coupling capacitor here, it's not as obvious. Basically, the low impedance side is where the signal is coming into the capacitor, and then it goes out to the grid of the next stage, which is high impedance. You can see all the resistance here. So your signal is coming from the plate, which is low impedance, going in through this capacitor, and then going into the grid of the next stage, which is high impedance. So this being the low impedance side of the circuit, and this being the high impedance side of the circuit, we want our outside foil to be on this side of this 1 nanofarad bypass capacitor. So that's how we orient the outside foil. By doing that, it gives the induced hum and noise the easiest path to drain off through ground, rather than going through to the next stage of the circuit and consequently being amplified. And if you have that hum coming in at every stage, it's additive. So by the time you get past the master and into the phase inverter, for example, you have hum that has added and amplified, and you can have quite a bit of noise, hum, that kind of thing. How do we find out which is the outside foil on a foil capacitor? So I've got here an example of old capacitor. This is out of an old mid-60s 64 Baseman. That's another one of my favorite amps, the 64 Baseman. I'll probably do a video on that at some point too. This is one of the famous blue molded foil capacitors, and I don't know if you can see, maybe you can see it on the overhead camera here. At one end there is a black line at the end of the label here. You might not be able to see that, but trust me, it's there. That black line is supposed to identify the lead that has the outside foil connected to it. I've tested a lot of these. It's not always the case. I think if it was a Monday morning and the person working on the line making capacitors was very hungover because it was early Monday morning, they could get that jacket on there wrong and identify the wrong lead as having the foil attached to it. Likewise, if it was Friday afternoon, last thing, they're all getting ready to go get hungover, they might not have been paying attention, and so they subsequently got labeled wrong, and that's pretty common to find. So I don't know when people first discovered that the outside foil would act like a shield. It seems kind of like an obvious assumption when you know how the capacitors are designed and how shielding for noise works. But along the line, someone came up with the idea that, hey, in an audio circuit, we could make this quieter by putting that foil to ground. So I guess for that reason, they started marking the outside foil, or that was their intention. But discovering that mark is not always correct, some smart guy came up with the idea to use his oscilloscope and check which end the foil was connected to by looking at how much noise was induced by connecting the capacitor to the oscilloscope, and just looking at how much noise is induced when you grab that from the background noise and your body acting as a big antenna. It will couple all of that noise into the capacitor and then through into the circuit, through the clips into the oscilloscope. So my real oscilloscope died a couple months ago, and I haven't had time to troubleshoot that yet, but I do have a virtual oscilloscope, a USB-based oscilloscope. You might hear this fan noise going in the background. I have an old notebook computer here that I run my oscilloscope software on, and that fan is a little bit loud in there, so apologies for that noise. So what we're going to do is we're going to take a new capacitor. I've got one of these yellow capacitors. It's a 1 nanofarad. I'm going to connect the oscilloscope probe to that capacitor. And I've got my oscilloscope showing me the noise on the screen. This is the basic noise, just the background noise that comes in there. It's 60 hertz because that's what we run on here in North America. At any rate, I have the probes connected. Now the idea is that if the outside foil is to ground, it will shunt off all of that induced hum and noise when I grab the capacitor, and your waveform will be a certain voltage level, usually a few millivolts. If I have the foil to the side of the probe that is positive, or the hot side, you would see an increase in that induced voltage. Still only a few millivolts. It can be actually quite difficult to tell which lead is connected to the foil on the larger capacitors. I'll show you that later. At any rate, I don't know which end the foil is on this capacitor right now, but I do have it connected. If you look at my oscilloscope, I'm going to grab this foil capacitor. You want to be careful that your fingers don't touch the leads. That will make a lot of noise no matter which way around you have the capacitor. So being careful not to touch the leads, I'm going to grab that capacitor with my fingers and pinch kind of firmly. Now if you look at the oscilloscope, you see I've got a peak to peak. It's around 1 millivolt, 0.9 millivolts peak to peak. Here I've switched the leads, and now I'm going to grab that capacitor again, and you see that we have a voltage induced there, about 1.2, 1.3 millivolts. Only about 0.3 millivolts of difference, but clearly it is there's more noise induced into the system with the orientation this way. That means that the positive probe of my oscilloscope is on the lead that is attached to the outside foil. So once again, we look at that. We've got 1.3 millivolts, 1.2, 1.3 millivolts. I'm going to switch this back and do the same thing. I'm going to pinch the capacitor between my fingers, and we're at about 0.9 millivolts. Yeah, it's staying pretty steady at 0.9 millivolts. So this is the quietest orientation. What that means is the ground probe is on the outside foil. So we take a Sharpie marker and we just put a little mark at the end. When we go to use this capacitor, we know that that's the foil end. That should be connected to ground or to the low impedance side of the circuit. So let's check a couple more. I've got another 1 nanofarad orange drop sitting here in front of me, and I will connect the leads, and we'll see what we get on the oscilloscope. This is a 1 nanofarad orange drop, and the yellow one was a 1 nanofarad. You'd think we'd get the same voltage induced, but they're different devices. Even device to device, your voltages might not be the same. But let's see what we get. I'm going to pinch this, again being careful not to touch the leads. And what I get is a peak of 0.5 millivolts. So I will reverse this and grab that. I get a peak voltage of about 1.2 millivolts. So that's noisier than the other orientation. So what that means is the hot probe of my oscilloscope is actually connected to the side with the outside foil. So I'll put a little dash there, or a little line there, and then I know that's the foil side. So looking at this again, I haven't changed it. I grab this. We get about a 1.2, 1.1 millivolt peak to peak. I'll switch the leads, and same thing, pinch the capacitor, and I get about 0.5 millivolts. So I do know that this is the outside foil. As you're checking bigger capacitors, that difference gets much smaller. By the time you get to, say, 0.1 microfarad capacitors, you essentially cannot tell the difference. In that case, I don't really worry about it. If it looks like one side's quieter than the other, I'll mark it, but I'm not too concerned at that point. It's just as quiet either way. The truth about this is your foil capacitors are not really polarized in any sense that the circuit needs them to be polarized. It doesn't matter which way they go into the circuit, it's going to work just fine. You'll just have a little bit more noise one way than the other. So let's go check here. I've got 3 more orange drop capacitors. I've got a 33 nanofarad, I've got a 47 nanofarad, and I've got a 0.1 microfarad. So let's connect the 33 nanofarad, and let's see if we can tell a difference in the induced noise. So I've got my ground and my hot connected to this capacitor. Right away, what you see is we don't have as much background noise showing up on the oscilloscope screen. So if I grab that, I can see that it's getting a little bit of noise. The stats down there are saying peak to peak I'm getting 0.1 millivolts. So I will reverse these leads and see what I get the other way. I might only get 0.2 millivolts. Yep, peak to peak, actually here it's flashing between 0 and 1 millivolts. So I would say that's the quietest side, although it did stabilize at 1 millivolt. So I'm going to switch this back again, and it's still showing 1 millivolt, but it's fluctuating between 0 and 1. The resolution on this scope is not that good, so I'm going to say that I've got the ground lead on the quietest side. That really is a guess. If you really want to try and get a good picture of this, you can take an AC cord, and you don't have to plug this AC cord into any device or anything. You just plug it into your wall socket. Make sure you don't have bare wires. We don't want that kind of excitement. And then what you can do is you can lay the AC cable across the capacitor, and that will induce a little bit more noise. With this orientation, I've still got a 0.1 millivolt peak to peak signal. I'm going to switch the leads. Now I've got a 3 millivolt peak to peak signal. So that did help me identify the side that has the foil attached to it. So right now with a 0.3 millivolt signal on it, that would say to me that the hot lead of the oscilloscope probe is on the foil side. Let's reverse this and see what happens. So yes, I've reversed that, and now it's bouncing between 0 and 0.1 millivolts. So I would say then that the foil side of this capacitor is on this side, because that was our 0.1 millivolt signal we were getting induced, and that's where the ground clip is. So that little AC cord trick can help. Let's look at this 47 nanofarad, and we'll see what we're getting on that. We'll do the same thing. We'll use the AC cord to try and get a little bit higher noise level. I'm sure there's other ways we could get a higher noise level induced in there. At any rate, here we've got the leads clipped on. I'm laying that AC cord across the capacitor, and I'm getting a 0.1 millivolt signal again. You can't even hardly see it on the oscilloscope. There's a little bit of rippling there. Let's switch these leads and see what happens. It's showing me a flashing between 0.2 and 0.3 millivolts now. I can see on the oscilloscope the waveform is taller, so I'm going to say that the hot lead is definitely connected to the outside foil. I'll reverse this again, and yes, I'm back to about 0.1 millivolts. So let's go up to a big 0.1 microfarad capacitor. Let's see what we can get out of that. So I've got my leads connected to this 0.1 microfarad, and I've got the AC cord on it, and you can see the capacitor initially charge up. Everything jumped up and then it gradually came down, but we do see some ripple, and we're getting 0.1 millivolts. Let's swap those and see what we get. And now we've got a little bit of ripple on there. To me it looks a little bit smaller, so I would say that this side is the foil side because that ground lead is connected. But to be honest about it, it's really hard to tell a difference with a capacitor this big. All right, well, that's great, you say, Jag. You got your oscilloscope and you're able to figure out where the outside foil is on your foil capacitor using your oscilloscope. I don't have an oscilloscope. What can I do? All we need is something that shows us what the amplitude or level of the noise is oriented one way or the other. So you can make a simple little jig using a guitar patch cable, and you just solder some clip leads to the other end. Clip off the jack and solder some clip leads on there. Make sure you know which one's the ground lead and which one's the hot lead. I always use green for ground, so I know that's ground. I just happen to have a yellow jack, so I used yellow. Normally you'd use a red. And then what you can do is you can clip your capacitor into that jig, and you do the same thing. You just plug it into the amp. I assume you can hear that noise. Okay, that's just the background noise. One thing I want to point out with this jig, what you want to do is you want to hold by the clip lead that connects to ground. You'll induce quite a bit of noise if you hold it by the hot clip lead. Just listen to this for a minute. So you hear how much louder that was when I grabbed the hot lead. So I always hold this by the ground clip. I've got the capacitor clipped in here. Ground is over here. I'm going to just pinch this, and you can hear the level increase. Okay, so now what I'm going to do is I'm going to reverse the leads. And we already had our marked end was at ground, so that should be the quietest orientation. We should hear a louder noise when we test it now. So there's the background noise again. I'm going to grab this. Yes, and it's quite a bit louder. Again, you can use your AC cord and do the same test, and you should get a little bit louder noise. So I've got this clipped in right now. I'm going to reverse the leads so that the hot lead is on the outside foil, and we're going to see how much noise we get. So that's the noise with the positive on the end we had marked with foil. Let's switch that and see if it is quieter with the foil side to ground using the AC test. And I'll pinch that. And yes, it's quieter. So we know that this is our foil side of the capacitor. And you can do all the same tests for the capacitors as they get bigger. I'm not going to go through them all now. I've shown you that on the oscilloscope. But let's, just out of curiosity, let's check the biggest one we're testing today, that 0.1 microfarad. I'm going to connect this with the hot on the side we marked as the foil side. And I'll do this with and without the AC cable connected. So first we'll do it just by pinching it, and then I'll reverse the leads and we'll see what the difference is. So, okay, right off the bat you notice that the background noise is much less. That's because the capacitor is so big. So I'm going to turn the volume on this up a bit. Actually, it's almost full, and I don't know if you can hear that, but let me grab the capacitor. So there, you heard an increase. Now let's reverse these leads and see if this seems any quieter with the ground lead on the one we've marked as the outside foil. Background noise. Okay, so we do hear a little increase in noise. To me, it doesn't seem like as much noise as there was with the ground lead or with the hot lead on the one we had identified as foil. So I'm pretty confident to say that this is the outside foil. What about if we use the AC method to test? I'm going to reverse this, and let's see what happens when we do this with the AC cord test. So there we are. Okay, we get a pretty good jump in noise there. Now let's reverse those, and this should be the quieter connection because I'm putting the ground on the side we've marked as foil. Yes, we get a little jump in volume, but not as much as with it the other way around. So this is the outside foil on this capacitor. So this test even works pretty well with even these big capacitors. As a matter of fact, I found the audio test, it was easier to tell that volume difference than when I was doing it with my oscilloscope. So that's how you test for the outside foil of your foil capacitors. As we said, we want the outside foil to go to ground when your capacitor is grounded, or we want it to go to the low impedance side of the circuit when your capacitor isn't connecting to ground. And generally the low impedance side of the circuit would be the plate side, and then the signal will go through that capacitor. From that point on, you're on the grid, the input side of the next stage. So I hope you found this interesting and helpful. If you enjoyed this, please smash that like button down there. That helps with the algorithm and it helps me a lot. Please check out my band, One Soul Thrust. All the links are below, as always. If you like what you see and what you hear with One Soul Thrust, please consider supporting us on Patreon. The link to Patreon is down below as well. Thanks for watching, and we'll see you again. Don't forget, the next video I will have the Triwatt completed and ready for testing. Might even be making some sounds with it.